Welcome you all in this session. Okay. Now, one problem that I will try to solve with the help of finite element method. Suppose we are taking here the diffusion process in the form of a steady state approach only. So for this, suppose we have this is the solution region in the one dimension case, and we discretize this length. C is equal to 10 and dc by dx is equal to 3. That is the given your boundary conditions. And we discretize this solution region with the help of 5 nodes and the 5 nodes that we define, and number of element is 1 less, it is 4. You can extend this 5 to 50, 500 according to problem. So one element information can be generated. So for every element, it has 2 nodes, 1 and 2. So locally, for every element, you have 2 nodes, 1 and 2. But in global form, for every element, the node information is different. Suppose we are talking about here. So it has the global node, it is 3 and 4, but locally it is 1 and 2. So once we are solving local in nature, node information will be 1 and 2. But once we assemble, it has the position between 3 and 4. So this is the third number of element that we are talking about. So accordingly, we will handle all the element. So number of elements are 4 here, 1, 2, 3, 4. You can extend accordingly. To understand the finite element method, we have used the most simple problem. Now, after defining, we define the interpolation function. Okay, so the node information accordingly x1, x2 that can be defined. Okay. So the interpolation function that we defined here, n1c1 plus n2c2. It will lie between 0 to 1, that you can say accordingly. Okay. C is equal to n1c1, that can be represented in the form of matrix n1, n2, c1, c2. This is your problem that we have defined. What is n1 and n2? N1 is what? x2 minus x by l. L is the length of the element. And n2 is what? X minus x1 upon n. So you can see if x is equal to x1, the total length that will be there, x1. So that can be defined in the form of this one, in this way. And n2 for x is equal to x1, it is 0, and then x is equal to x2, it is L. So it will define in such a way. With the combination of these two, we frame the what? Interpolation function for the one dimension case. Now this diffusion equation can be defined in such a way: d by dx, d dc by dx plus q is equal to 0. After defining the interpolation function, okay, this c is now written as in the form of nc. So in the place of c, we can have the nc. This is the single element information. There are a number of ways to get the weak form of the equation, such like weighted residue method, Galerkin approach, Ries approach. So according to the equation, according to mathematical model, you can go through accordingly. First, I will see here the weighted residue method to have the information for the each and every element. So in the place of C, we write here NC in the interpolation of polynomial form. Once we write NC, it will have some error, so it cannot be equals to 0. So what we see, some residue that we can define here. So in the weighted residue, if we have integration of WR dx is equals to 0, so it can be represented in the form of weak form. So R is replaced by this one. Okay. Now we will see the Galerkin method here. In the Galerkin method, in the place of W, we have used here N transpose. N is the matrix that was represented by N1, N2. So this is a difference between weighted residue and the Galerkin method. So now, according to this formula, the integration by part that we can, integration of uv that we can see here. So integration of u dv that can be applicable here. U is what? U is nt, and dv is what? This whole term that we can represent as a dv, and this is your u. So by having this, what we get? This formula we have used here, and plus integration ntq dx that we can see. So by solving this, we get this information. Integration of d by dx nt d dncx dx. It is what? It is integration of ntq dx plus nt d dncx upon dt. For some boundary condition can be applicable. So what we see, according to this, the derivative. Now n is can be written in the form of matrix form. So n transpose also can be written in the matrix form. So n transpose, that is n1, n2, dnc upon dx. So d upon dx, nc is what? n1, n2. That can be written n1, n2, and c1, c2 dx. So what we have done here, the whole problem is represented in the form of matrix here. Now, this can be written as, if your function is smooth, so it is integration, we can write d upon dx n1, d upon dx n2, and this can be written in the form of d of n1 dx, d of n2 dx, and c1, c2 that can be handled here. Finally, the whole matrix, once you multiply these two, it can be written in the form of integration of dn1 x squared dx. So multiplication of these two, then these two, and accordingly matrix multiplication is applicable. So finally, it is what we get. It is in the matrix form we get here. It is only ax I have written. Later on, we will go for b. Okay. So you know n1, n2 is defined in such a way. So dn1 upon x is minus 1 upon l. dn2 upon x is 1 upon l. So accordingly, you can define here. So integration of dn1 upon dx squared dx is 1 upon l, and same way we can write here. Now, for every, it is for c1, c2 that we can write for the one element. If you go for the globally, so it is 1, it is 2, it is 3. So it can be changed. C1, C2 can be changed by C2, C3. And this matrix is common for each and every element here. Now the second part, integration ntq dx was left. So it is what? Q integration of n1, n2 dx that we can see. So it is what? Q integration of n1 dx and integration of, it should be n2 dx. So it will be what? It is q l by 2, q l by 2 that we can write here. So by having 1 and 2, what we get? The matrix information for one element that we get here, information in the form of matrices. Now, it has some value. D has some value. Q has also some value. So what we get here for element 1, it is written as 1 upon L, minus 1 upon L, minus 1 upon L, and 1 upon L that you can see here for the first element. If you go for the second element, what we get, everything is same, only the information of the element is changed. From C1 to C2, it is what? It is for second element, so it is C2, C3 that can be written here. And the same process is applicable for all 4 elements. Can I? Just a minute. Okay. Same way, you can go for the element 3 and 4. So in this way, we will have the element information for each and every element. Now, the next term is what? Assembly. So the local matrix can be defined here. So you can see D is multiplied by each and every term. So what we see, for every element, we will have the coefficient matrix in such a way. Now the next is we have to assemble all the local matrix and we have to frame the global matrices. So some animation we can do here. So it can be added here. So as you know, it is the element information for 1 and 2 and 3, 1, 2 and 3. This third will be there. So it can be increased. It is by 4 and it is by 4. So all information is added accordingly. So what we see, the nodes are there. So nodal information globally that we have obtained by assembly of the matrix. And in the right hand side also the same manner we will give the values. So this is in the form of that we can say AX is equals to B. So mathematically we understand AX is equals to B, and for the engineering point of view it has a different name discussed earlier. Now we apply the boundary condition. C1 is given is what? 10. So it is 10 and TC by DX is equals to 3. So that is DQL. Sorry, QL by 2 plus 3 that is added here. So once we solve this system application, we will get the element information for whole 5 nodes. So in this way, we can obtain the value or solution for the all 5 nodes. You know, the some error can be definitely have some mistakes can be done. Okay, so in last few minutes, I will talk about the convergence of the method. So approximation of the element is very well defined according to finite element method, but the thing is your solution should be converged. The convergence of the solution is very important, so that it will match with the exact solution or it is close to the exact solution. So mesh refinement can be done. The one way is mesh refinement can be done. Some necessary condition for the FEM method to converge as follows. The continuity. The trial solution and the weight function are sufficient continuous. As you know, the element information that we say, if it is the linear, if it is linear, then it can be written as U is equals to C1 plus C2x. It is the continuous in nature. You can write C3x squared if it is quadratic form. If you are writing here, second thing is completeness. So the trial solution and the weight function must be able to capture a given smooth function with arbitrary accuracy. So the kth degree of freedom that is required according to the problem. So what do we see? The suppose A1 plus A2x or C1 plus C2x is written. It has the first degree of freedom. So number of it has a linear completeness that we can say. It can represent any first degree linear polynomial. Same way, if we go for the quadratic, the second degree polynomial, so it will have the second degree completeness. It can represent the quadratic polynomial. It means what? The function itself and its derivative is also continuous. Accordingly, that can be handled. But if we write in that way, A0, A1x and A2x4 is the first degree completeness, because it cannot represent all the quadratic, cubic and quadratic polynomials. So this approximation will converge as fast as a linear approximation. So that can be think of the according to element information, you can talk about the convergence. Now come to the refinement. some finite element analysis is also required. So number of type of refinement can be done here. One is H refinement. If we reduce the size of the element, then you can refine accordingly. P refinement is what? If you increase the order of the polynomial on an element, linear, quadratic. So it refers in this way also you can refine the element information. R refinement is what? Rearrangement the nodes in the maze. If you shifting the node accordingly, so it is according to the this one also you can refine. One is HP refinement, the combination of H and P refinement, that will be a better result. But once you refine the element information, you must think about the computational cost as well accordingly. Suppose we talk about this kind of information. What we see here, the 4 nodes are there and 2 elements are there. But you have increased the number of elements. So it is 1, 2, 3, 4, 5, 6, and 7, 8. So in the same structure, you have defined the 8 number of elements. You can increase, it is a 32 elements. It is 32 elements accordingly. So the maze refinement can be done in such a way also. But the thing is, what we see in each and every refinement, the original node is not replaced. Original node is together, even though you have increased the number of element. But the next, what we can see here, the 6th element is there.